Section 2.4, limits at infinity. So let's just jump right into the definition here. If f of x becomes arbitrarily close to a finite number L for all sufficiently large and positive x values, that is x growing without bound, then we write this: the limit as x approaches infinity of f of x is equal to L. Okay, so this sentence is very mathy and wordy and kind of confusing. Since we're becoming more familiar with this limit notation and just the concept of limits and how they work and what it means, I feel like this is the easiest way to communicate what an infinite or what a limit at infinity is. We're letting x become very, very large in the positive direction and seeing what happens to the output values of the function, right? If it converges to some finite number L, then we say that the limit at infinity exists and is equal to L. Similarly, if f of x approaches some number m as x decreases without bound, we write the limit as x approaches negative infinity of f of x is equal to, to m in this case. All right, so now we're looking at limits where x values are getting infinitely large or infinitely small. If one or both are satisfied, the line y equals L or y equals m is a horizontal asymptote. Okay, so in the previous section, we're looking at infinite limits, and we saw that those infinite limits, if we had them for a function f, they corresponded to a vertical asymptote. Now we're seeing that limits at infinity, where the input or the independent variable is going to positive or negative infinity. If that converges to some real number, that gives us a horizontal asymptote. So here's a little picture. This should look familiar. You should have seen horizontal asymptotes before. These are just lines to which the function converges in the long run. And, one kind of falsehood that gets spread about horizontal asymptotes is that they're a line that the graph never crosses. This is true about vertical asymptotes because, if we have a vertical asymptote at x equals a is not in the domain of the function f, right? So it really does never cross that vertical line. But horizontal asymptotes, that's not always the case. Sometimes we can cross over them. Really what it means is as x gets really large, the graph of the function is going to get really close to it. Okay. Another way that we could, or another name for the behavior of a function as x gets really large or x gets really small is end behavior. Okay, so you might hear me say that in reference to infinite limits. Okay, so an important kind of conceptual question here. What happens to a fraction as the denominator gets very, very large? So let's say we have a fraction, let's say it's just 1 over a really big number. What type of number is this? If you take 1 and divide it by a big number, very generally speaking, this is going to be a very small number. Okay. So if we're looking at a limit like this one in this next example, the limit as x approaches infinity of 3 over x squared. Okay, so the numerator is a constant, and actually there's a typo. I think this should be if the numerator is a constant. Because if the numerator were also a variable, like if it was an x, then numerator and denominator would both be going to infinity, which is not so obvious or clear or determined what's going to happen. Okay, so looking at this example, this is what we mean. The numerator is a constant value. And since we're taking the limit as x goes to infinity, this denominator is expected to get very, very large. So we want to use a table of values. And we've evaluated limits in the past using tables of values. The way we did it before is we would have x approaching some real number. Like here, we did one in this last section. Yeah, this is from the last section, 2.3. We were looking at the limit as x approaches 5. So we had a table of values that looked like this. We were deliberately picking these x values really close to the left and to the right of 5. So our strategy is going to change a little bit when we're looking at an infinite limit. So rather than plugging in values that are getting really close to some real number on the x-axis, we're going to just be plugging in really big numbers. Like maybe we'll start with 10, and then maybe we'll plug in 100, and then maybe 1,000. Okay, and maybe we'll go even bigger than that if it isn't clear what's going on. But let's do this. Okay, so if I plug in 10, I get 3 over 10 squared, which is 3 over 100, which is, as a decimal, 0.03, right? That's 3 hundredths. Okay, let's plug in a bigger value. So if I plug in 100, so 3 over 100 squared, this is going to be 3 over 10,000. All right, and 3 10,000ths, that's like this, 0.0, so that's hundreds, thousandths, 10,000ths. Okay, let's do one more. If we plug in 3 over 1,000 squared, that's going to be 3 over a million. Three millionths. Okay, what does this look like as a decimal? Okay, tens, hundreds, thousandths, 10,000ths, 100,000ths, millionths. Okay, so the inputs are going towards infinity, right? That's what we're trying to simulate here. What does it look like is happening to the output values? It looks like they're getting really, really close to 0. Right? I can see that this decimal is just going to keep getting, more and more zeros. It's always going to have a 3 on the end here. So I can see that this is just getting closer and closer to 0. So as x approaches infinity, f of x appears to approach 0. So that's why I'm going to say that this limit, as x approaches infinity of f of x, which is 3 over x squared, this limit is equal to infinity. All right, so the table of values approach, it's not always the best approach just because notice that we're kind of like inducing that this goes to 0. Like we're not ever going to see it go to 0, right? Because I can't count all the way up to infinity on a table of values. We're just kind of inducing that it goes there. So table of values, it's not like the bulletproof method for evaluating limits, but it's really good for just kind of seeing the mechanics of what's going on and understanding like, okay, I can sort of conceive of, as these x values get larger and larger and larger, the output values are going to get smaller and smaller and smaller, closer to 0. All right, and it turns out that this is going to be the case whenever we're in this situation where we have a constant value in the numerator and then just x to the power of some constant k in the denominator. And if the limit is going to positive or negative infinity, it doesn't matter which one, it's going to go to 0 in both cases. Okay, so the simplest kind of situation, I guess aside from just having a constant function, is if we have something in this form, a constant over x to the k power, and x is going to infinity. All right, so if we wanted to evaluate a limit like this one, and really there ought to be grouping symbols, we're taking the limit of this sum here. So we're looking as x goes to infinity of 7 plus 5 over x plus 9 over x squared. So that's a whole sum that's happening inside of a limit, but we don't have to be too deterred or inconvenienced by this, because we have this rule which we learned in section 2.2. The limit of a sum is equal to the sum of the limit. So I could break this into a bunch of separate limits. So this is the limit as x goes to infinity of 7 plus the limit as x goes to infinity of 5 over x plus the limit as x approaches infinity of 9 over x squared. This is helpful. We can just take the limit term by term. So what happens to each of these? So first of all, the limit as x goes to infinity of 7. There's a rule, whenever we take the limit of a constant, it's just going to be equal to that constant. This is just going to be equal to 7. Graphically, if we're looking at, the function y equals 7, this is just a horizontal line at x equals 7, so it's just like this line, right? It just outputs 7 no matter what. So as x goes to positive infinity, what is this graph gonna output? It's just gonna output 7. That's all that it does. Okay, so that's why we got 7 there. Moving on, what about the limit as x approaches infinity of 5 over x? Well, this is in this form, right? This is just 5, in the form a over x to the first power. So 5 over x to the first power. And you can imagine doing a table of values. What's going to happen to the value of this as the denominator gets really, really big? It's going to go to 0. Okay, turns out the same thing happens for this last limit here. That also goes to 0. So this limit is just going to be equal to 7, and that'll be our answer. Okay, so that's, a very specific case where we're looking at a limit as x goes to infinity. We're not always going to be dealing with functions in that form. Sometimes we'll have polynomials. That's what I want to look at next. So remember, with polynomials, we graph them. We did this kind of thing in pre-calculus. And when graphing polynomials, one really important feature to look into is the end behavior. Okay, and the end behavior of a polynomial is determined by that first, that leading term. So remember, if we have a leading term which has an even power on x, this means that the polynomial has an even degree. And what that means is that the end behavior is going to be going in the same direction, right? It's going to be going up and up, or if that leading coefficient is negative, it's going to be going down and down. Okay, and whether it goes up or down depends on the sign of the leading coefficient, okay? However, if the degree of the polynomial is odd, then we have this type of end behavior where it goes down on one side and up on the other side. That's if we have a positive leading coefficient. If we have a negative leading coefficient, then it's going to go up to the left and down to the right. All right, so back in pre-calculus, you were just sort of told what the rules were, and you were expected to trust it and use that to come up with your graphs. Okay, but it turns out really it's calculus, or it's the limit that allows us to explore that topic of like what happens to the value of the function as x gets really, really large or really, really small. Really, we're talking about infinite limits here. Okay, so if we wanted to find a limit, like, okay, the limit as x goes to infinity of x squared plus 2x plus 7, you could use a table of values. Okay, I'm not going to be mad at you if you do this to check your work. All right, you could do the thing, we're looking at x going to positive infinity, so we could plug in 10, 100, 1,000. Okay, you could do this and see what you get. For this one, if I plugged in 10, I got 127. I did this on my calculator earlier. 100, I got 10,207. I didn't even bother with 1,000. You could see that this is getting really big, right? These are big numbers. So it looks like this limit is going to positive infinity. Okay, but I actually happen to know what this graph looks like roughly. Like I know the end behavior of the graph. Since it is even degree, right? The highest power on x is an even number. I know that I'm going to have behavior that is either up on the left and up on the right, or down on both sides. The leading coefficient in this case is positive 1. So since that's a positive number, I know that it's going to have this type of end behavior. All right, you could also plug this into your graphing calculator, see what the graph looks like, but you're going to see a parabola, right? So the graph will look roughly like this. I don't know exactly what it's going to look like, but it's going to have that kind of shape. It's going to be parabolic. So since I'm looking at the limit as x goes to infinity, that's just saying, you know, what's the end behavior on the right-hand side? I could see that it goes to positive infinity. Okay, so the limit as x approaches infinity of x squared plus 2x plus 7 is equal to infinity, positive infinity. All right, so just a few more details on that kind of trick, that shortcut that I used there. Here it is. Okay, so assume that n is positive, right? And really it's a positive integer. So we're looking at the limit x approaches infinity of x to the n. If n is even, then that means that the limit as x approaches either positive or negative infinity. It doesn't matter which one, works the same for either of them. That limit of x to the n is going to be equal to positive infinity. Okay, and then if n is an odd number, right, think about the behavior, the end behavior of polynomials which have odd degree. The limit as x approaches negative infinity of x to the n is going to be negative infinity. And the limit as x approaches positive infinity of x to the n is going to be equal to positive infinity. All right, because if the degree is odd, then we're thinking about this type of picture here. All right, and then if we multiply, like if we have a negative leading coefficient, that's going to change the signs of all of these, right? So this will apply to any polynomial, and in general, we will use the leading term. The leading term to determine whether it's positive or negative infinity. All right, so we've got a few examples to do here. This first one. Okay, the important details here. X is going to positive infinity in this case. Here's our polynomial. I really only care about the leading coefficient here, right? So the leading coefficient tells me that n is an odd number, right? So the degree of this polynomial is odd. And the leading coefficient, so I could also call this the degree. And then the leading coefficient in this case is 5, right? Just being whatever, that x to the n is being multiplied by. And the important thing to note here is that this is positive, right? It's greater than 0. It's a positive number. So since the degree was odd, I know that it's either, the behavior either looks like this or it looks like this. But since I have a positive leading coefficient, I know it's going to be this first one. So I know the graph looks roughly like that. And I'm looking at the limit as x goes to positive infinity in this case. So I'm interested in this right branch, which I can see as going up to positive infinity. So I can answer this. The limit as x goes to infinity of 5x to the 7th plus 7x squared plus 1 is equal to positive infinity. So you can check your work using a table of values if you'd like. But as long as you're comfortable determining the end behavior, you can use that as a shortcut. So really we're relying on our pre-calculus knowledge of polynomials and their graphs to answer these a lot more quickly. Okay, so this next example, same function, except we're looking at the limit as x goes to negative infinity. So we're still thinking about the same type of end behavior. We know it's going to be down to the left, up to the right. So now we're looking at the behavior in the left branch of the graph, right, as x goes to negative infinity. So this is what's going to tell us what this limit is equal to. We can see the graph is going down to negative infinity. Okay, and by the way, you can check your work with a table of values. If you want to check what's happening to this function as x gets really, really big in the negative direction, plug in negative 10, negative 100, negative 1000. Okay, and you should see that these values are going towards negative infinity. Just another way to check your work if you're not confident. All right, a couple more down here. This next one, we're looking at the limit as x goes to infinity of this quadratic. So here's our leading term. So I see that n is even. Okay, so that means that this is going to have end behavior up and up or down and down. Now, which is it, up and up or down and down? Well, the leading coefficient in this case is -3, which is less than 0. That's a negative number. So that means that our end behavior is going to be down and down. So whether the limit is going to positive infinity or negative infinity, doesn't matter. It's going to be negative infinity either way. Okay, so this one, limit as x goes to infinity, -3x squared plus 2x plus 7. It's going to be equal to negative infinity based on the end behavior of the function. All right, pretty straightforward so far, I'd say. For this last one, we're looking at the limit as x goes to negative infinity of x squared times x plus 2. I can tell this is a polynomial, but it's in factored form, which sometimes we like factored form, right? It makes it easy to find zeros and stuff like that. But for these types of problems, we want to know what the leading term is so that we can, determine what the end behavior is and use that to figure out what the limit is. So I'm actually going to multiply this one out. Okay, I would much rather look at this in general form, is what we call it. Some books call it standard form, but I'm going to multiply it out. I'll just distribute this x squared, and here's what I get. I'm looking at the limit as x goes to negative infinity of x cubed plus 2x squared. All right, so sometimes I can trick students by doing this kind of thing, and they see this and they think, it's even degree, right? The highest power on x that I see is a 2, so it's even degree, and they might make some assumptions based on that. But we can only determine the degree when we have everything multiplied out and it's written in general form. This is the real, true leading term. And from this, we can see that the degree is actually 3, so it's an odd number. The leading coefficient is just 1, which is positive. So that means that the end behavior is going to look like this: down to the left, up to the right. And I'm looking at the limit as x approaches negative infinity. So this is really the part of the graph that I'm interested in. So I can see that it's going down to negative infinity. So the limit as x goes to negative infinity of x squared times x plus 2 is going to be negative infinity. You can check this with a table of values if you like, but I'm pretty confident in that one. Okay, so moving on to the next kind of subtopic here. What happens if we get a limit that is outputting infinity over infinity? All right, this is kind of an indeterminate situation here, right? Because like the denominator is going to infinity, and in the past when we saw that, we thought, this number must be getting really, really small, right? If the denominator is getting really, really big. But what if the numerator is simultaneously getting really, really big? Okay, so how do we deal with that? That's what we're going to look at next. So finding limits at infinity or end behavior of rational functions. That's what this is going to come down to. Rational functions being functions in the form p of x over q of x, where p and q are both polynomial functions. So our method for this is, first we're going to factor out the highest power x to the k that appears in the denominator. And we'll get a cancellation from that. And then from that, we should be able to compute the limit using algebraic properties of reciprocal power rules. So that's what we're looking at up here. These are the reciprocal limit rules up here. Okay, let's see an example. You'll get it. So here's one. We want to find the limit as x goes to infinity of x squared plus x plus 1 over 3x squared plus 7x minus 3. All right, so what we do is we want to start by identifying what is the highest power x to the k that appears in the denominator. All right. Oh, and by the way, like to test, if we tried to just plug in infinity into this thing, like what would happen? It turns out that the numerator and denominator would both end up going to positive infinity, right? Since these are both quadratic and they both have positive leading coefficients. So, without doing anything, this goes to infinity, this goes to infinity. So this is the infinity over infinity case here that we were worried about. Okay, so since we're in that situation, highest power x to the k in the denominator is x squared. So here's what I will do. I'm going to factor out an x squared from the numerator and denominator. And here's what it'll look like. So we're still looking at the limit as x goes to infinity. So if I pull out x squared, remember when we factor out a common factor, what we do is we write it on the outside and then we divide each of these terms by whatever we're pulling out. So x squared divided by x squared is going to be 1 plus, and then x over x squared, that's just going to be 1 over x. right? Because if we're dividing x divided by x squared, see how one of the x's just cancels out? We're just left with 1 over x. Okay, and then dividing 1 by x squared, that'll just be 1 over x squared. So this might look kind of strange. You probably or maybe haven't done this before, but we'll see there's a reason we're doing this. Okay, same in the denominator. We're going to factor out x squared, and here's what we're left with. 3 plus 7 over x minus 3 over x squared. Okay, so that's just dividing each of the terms by x squared and writing the x squared on the outside. Okay, so now you see we have this common factor of x squared in the numerator and denominator, so we can cancel those out, or in other words, they make a big 1, right? X squared divided by x squared is just 1, so those can go away. All right, so now we have the limit as x goes to infinity of just this stuff. 1 plus 1 over x plus 1 over x squared, and so on. So you're probably thinking that this looks worse than it did at the very beginning of the problem. But this actually looks a lot better to me because we're looking at the limit as x goes to infinity. And remember, whenever we have something in this form, a over x to the k, and x is going to infinity, that denominator gets really big, which means this whole thing goes to 0. And we have a whole bunch of stuff in that form, constant over x to the k. So this is going to go to 0. This is going to go to 0. This is going to go to 0. And so is this. So when I actually evaluate the limit, everything's going to go to 0 except for that 1 in the numerator and that 3 in the denominator. So this limit is just equal to 1/3. Okay, you are welcome to graph this function on your graphing calculator if you want to see what the graph looks like. But what it's going to look like is I think it's going to have a couple of vertical asymptotes. I'll have a couple of vertical asymptotes. I don't know exactly what it looks like, but it might end up looking something like this. But the important thing is what happens is you're going to see that these converge to this horizontal line, y equals 1/3. So the horizontal asymptote is going to be y equals 1/3. Okay, so the long run behavior of this function is going to approach that horizontal line. Okay, let's try another one of these. It's going to be the same kind of procedure here because, yes, if we plug in positive infinity, numerator is going to go to infinity, denominator is going to go to infinity. So this is that kind of indeterminate form where we're going to have to do something tricky to make it so we can evaluate this limit at infinity. So let's run this procedure, right? What's the highest power x to the k that we have in the denominator? I think it's that x to the third. All right, so I'm going to factor out that x to the third. So I'll pull out x to the third. So in the numerator, if I pull out x to the third, 4x squared divided by x to the third, the x squared is going to cancel it out. I'm going to be left with an x, a factor of x in the denominator. So I'll have 4 over x. And then I'll have plus 2 over x squared. And the denominator, when I pull out x cubed, I'm left with 3 plus 2 over x. Okay, and I can simplify the x to the third power. Those can cancel out. And I'm just left with this. All right, and anything in the form a over x to the k will go to 0, so that goes to 0, that goes to 0, and this also goes to 0 in the step that I actually evaluate the limit. So after evaluating the limit, I'm going to get 0 over 3. So that's just equal to 0. All right, so graphically we should see in the long run, the graph of this function f should be approaching the line y equals 0, or the x-axis. Okay, something I want to point out quickly here. Sometimes when I'm grading students' work, I see the limit symbol disappear at a certain point. Like students just get tired of writing the limit as x approaches infinity or whatever. And that's a problem, because this limit is actually indicating that there's a certain operation that we have to perform, and we can't drop that limit as x goes to infinity, or limit as x goes to a, whatever a is. We can't drop that until we actually evaluate the limit. So notice that from this step to this step, this is where I actually evaluate the limit, let x go to infinity, all of those fractions go to 0. So be sure not to drop this, right? Don't stop writing that until you actually evaluate the limit, because you will lose points for doing that. Okay, so that limit went to 0. We've got one more of these examples here. Limit as x goes to infinity of 3x squared plus x over x plus 1. So what happens as x goes to infinity? That goes to infinity. Denominator also goes to infinity, so it's that indeterminate form. Let's see what we can do here. Let's try to pull out the largest factor, x to the k, in the denominator. In this case, it's just going to be x to the first power. So if I do that, factor out an x from the numerator, I'm left with 3x plus 1. Factor out an x from the denominator, I'm left with 1 plus 1 over x. Okay, I can simplify x over x as just 1, so I can just write this as the limit as x goes to infinity of 3x plus 1 over 1 plus 1 over x. So I'm ready to take this limit as x goes to infinity. This goes to 0. But that is the only term that is in the form a over x to the k. So nothing else is going to go to 0. Like, what's going to happen to the numerator as x goes to infinity? What happens to 3x plus 1 as x gets really, really big? Well, if I plug in 1,000 for x, I get 3,001. Right? If I plug in 1,000,000 for x, I get 3,000,001. So notice this is actually going to infinity. It's getting really, really large. So the denominator is, overall, the whole entire thing is going to 1. So this is basically going to infinity over 1. But that's sort of a weird thing to write. Really, this is just approaching positive infinity. So sometimes we'll have rational functions which don't approach 0 at all, or they don't approach a real number at all. Sometimes they diverge and go off to positive or negative infinity, and that's what happens in this case. And graphically what's going on is we have what we call a slant asymptote. Okay, so the slant asymptote in this case is going to look, and this is again just a sketch. Slant asymptote will look something like that. We have a vertical asymptote at -1. And the graph has this kind of behavior like this. Sorry, very, very crude sketch, but you probably remember seeing graphs of rational functions that look like this, where they have one vertical asymptote and one slant asymptote. That's what we're seeing here. So we can see as x goes to positive infinity, the end behavior is going to shoot up towards positive infinity, like that. Okay, so graphs are really helpful in kind of qualifying and verifying your answer for these infinite limits, just by looking at the graph and seeing what the end behavior looks like. One last thing I want to point out about these three last examples really is, you might remember in pre-calculus when you were learning how to graph rational functions, when you were trying to figure out what the horizontal asymptotes were, or if there even was a horizontal asymptote, you would do this thing where you would look at the leading coefficients of the numerator and denominator. More specifically, you would look at the degree of the numerator and denominator, right? So if you let n equal the degree of the numerator and let m equal the degree of the denominator, sorry, sometimes my handwriting is a bit illegible when using this tablet thing. So n is the degree of the numerator, n is the degree of the denominator. So in this first example, notice that n is equal to m, right? The degree of the numerator and denominator are the same. And you might remember the horizontal asymptote in this case is going to be equal to the ratio of the leading coefficients. So the ratio of the leading coefficients, that would be 1 over 3. That's exactly what we got for our infinite limit. Right? The next example, we had the degree of the numerator, n, was less than the degree of the denominator, m. And in this case, we know from pre-calculus that the horizontal asymptote should be the line y equals 0. That's why we got 0 as our limit. And if the degree of the numerator, n, is greater than the degree of the denominator, m, then there is no horizontal asymptote. And in some cases, specifically if the degree of the numerator is 1 more than the degree of the denominator, so in other words, n is equal to m plus 1, that's when we have a slant asymptote. And that's exactly what we ran into in this problem. Okay, so I just want to sort of bring our attention to this, because back in pre-calculus, when we're learning how to graph these functions, these rational functions, we don't have limits yet, right? Like when I teach this class, like I'm dying to talk about the limit as x approaches positive or negative infinity, but we just don't have that knowledge yet, so we have to remember these rules. But it turns out that horizontal asymptotes, we can discover them by just looking at the limits as x approaches positive or negative infinity. Okay, so it's good that we now have this method. We don't have to worry about memorizing, degree of the numerator and denominator. We don't have to take up mental space with that. Just perform this procedure and you can figure out what's going on with the end behavior of rational functions. Okay, and why would we care about the end behavior of any type of function? Well, it turns out that functions are created because they're really helpful at modeling change in the natural world. Okay, the ultimate independent variable is time. Okay, so if we're trying to, in this next example, we're looking at a population of a culture of tumor cells. And we found that this population is modeled by this function here, which is a rational function. We would be very, very interested in what is happening to the population of this culture of cells, right? Is it increasing without bound? Is it going up? Is it dying off? Is it staying the same? How would we figure this out? So if we want to know what happens in the long run, this is essentially as t gets really, really large, right? As time goes on indefinitely. So mathematically, we can figure this out by looking at the limit of p of t as t goes to infinity. Okay, so let's do that. Let's look at the limit as t goes to infinity of 3500 t over t plus 1. All right, I know we're using t instead of x here. Everything's going to work the same way. If I try to just plug in infinity, the numerator goes to infinity, denominator goes to infinity. So we're going to have to use our little trick here. Let's find the highest power, in this case, t to the k. So the highest power is just t to the first, so let's factor that out. So I'm going to factor out t in the numerator and denominator, so I'll have t times 3500 up top, and then I'll have t times 1 plus 1 over t in the denominator. Those two t's can make a big 1 and they'll go away. So let's find the limit as t goes to infinity of the simplified expression, which will just be 3500 over 1 plus 1 over t. So what happens here as we let t go to infinity? Well, I know that 1 over t is going to go to 0, right? Because the denominator will get really large. So the whole fraction will go to 0. And what are we left with when that goes away? We're just left with 3500 over 1, or 3500. Okay? So what's happening here is the population of this culture, as represented by this function p of t, we see that as time goes on, as t goes to infinity, this is going to converge to a kind of terminal population of 3,500 cells. Okay? So what this means, or the term for this, is this means that the system has reached a steady state. Okay? Steady state, or, it's reached equilibrium. You'll hear that sometimes, but it's reached a steady state of 3,500 cells. Okay, so that's just an example of an application where we might want to apply this concept. And that's the end of this section. So up next, and this is going to be the final section of this chapter on limits, we're going to be looking at continuity, which is a very important kind of seminal topic here. So I'll see you back here in the next video, section 2.5.